Hi everybody. In this video, we're going to look at how we can model motion where the acceleration is not constant. So we'll look at how we can use calculus. We're told that at time 0, a particle p is at the origin, and then when t is greater than 0, its displacement is modeled here. We need to find the speed of p when p is moving in the direction of I, and then we need to find the magnitude of the acceleration when t is 0.25. And for part C, we need to show that p never returns back to the origin. So I encourage you to give this question a go yourself. Think about the relationship between displacement, velocity, and time when the acceleration is not constant. You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So we want to work out the speed of p. And we know speed is a magnitude of velocity. And velocity is a change in displacement over time. So to work out the velocity, we need to differentiate the I component and the j component with respect to t. So dr by dt, when we differentiate 3t plus 2, we'll just get 3. And I'm going to write the square root of t plus 1 as t plus 1 to the power of a half. And then we can bring this power of a half down, and we'll get minus 1, t plus 1. We'll take away 1 from this power, so we get negative 1/2. And then when we multiply it by the derivative of this in a function, we just get 1. So this will be the derivative of the I component. When we differentiate the j component with respect to t, we'll just get 2t minus 6. And this is in meters per second. And we want to work out the speed of a magnitude of this when p is moving in the direction of I. So if it's moving in the direction of I, it has no vertical change. So the j component will be 0. So therefore, 2t minus 6 will equal 0. T must equal 3. So the velocity, we can put this 3 into the I and the j components. We'll have 3 minus the 3 plus 1 is 4. 4 to the negative 1/2 will give us 0.5. So this will be 2.5. And then for the j, we'll have 0. So we'll have 2.5. So we'll have a 2.5 meters per second, okay? And for part B, find the magnitude of the acceleration of p when t is 0.25. So we know acceleration is the change in velocity over time. So now we just need to differentiate the velocity with respect to time. So we'll just differentiate this again. Well, the derivative of this term will just be 0. When we bring this negative 1/2 down here, we'll get positive 1/2 of t plus 1. And then we'll take away 1 from this power, minus 3 over 2. And again, the derivative of this inner term is just 1. And when you differentiate the j component, we'll just get 2. So when t is 0.25, so I can do all of this on my calculator, we'll have 0.5, we'll have 1.25 to a power of negative 1.5. And this will be 4 root 5 over 25. This will be I, and we'll have 2j. We want the magnitude of this acceleration. So we'll Pythagorize the I and the j terms. Working this out, we get the square root of that previous answer squared plus 4. And this will be approximately 2.03 meters per second squared. And then for part C, showing that P never returns back to 0. So we're trying to show that this displacement can never again be at point 0, 0. So 3t plus 2 minus 2 times root of t plus 1, if this is equal to 0, and we want t squared minus 6t equal to 0. Well, we can solve this j component. We'll have t lots of t minus 6. So t will equal 0 and t will equal 6. Well, we know it starts at the origin initially, but will the I component also be 0 at 6 seconds? Well, if we substitute the 6 seconds into here, will we get 0? Well, 3 lots of 6 plus the 2 minus 2 lots of root 7 does not equal 0. We'll have 20 minus 2 root 7 again does not equal 0. Hence, there is no solution, so it does not return back to the origin. Well, thank you very much for watching. I hope you found that useful. If you want more practice on further kinematics, you can download the lessons and my worksheets from my website, mrmathematics.com. I'll leave a link in the description below.